All right, hold on, grade 12s. I'm just trying to turn a lamp on here. All right, let's get started. Happy Friday. It's the long weekend. Should be excited about that, I would imagine. We're going to do one lesson before we get to the long weekend, though. We're going to talk about parallel plates today. We're going to split our lesson into two sections because my videos always end up being so much longer than I want them to be. So today I'm not going to go through all of the practice problems. I'm just going to do the introductory kind of deriving of the formulas. And then we'll do a small little review of all the new terms that we've learned because there's a whole bunch of new terms that we're learning in this lesson, as well as the past ones, and it's hard to keep track of sometimes. So we'll do that. And then I will post some Rebus puzzles on the classroom because, well, I'm going to say this sarcastically, you've all been responding so much on the Google Classroom to those, posting your guesses. You do a better job of that. But no pressure. I actually don't really mind. Anyways, so let me know if you want me to keep doing those Rebus puzzles, actually, because I will. My grade nines really like them. I know you guys like them, but I feel like maybe because we're not in the in-person sessions or the live sessions, which actually we should start getting back to doing those. So we'll plan for one of those next week. I just felt like this week it was a little bit unnecessary because we just did our assessments. We're just basically starting a new unit. Anyways, this is why my videos are always so long, because I end up just trailing off and talking about whatever. So let's get right into it. We'll talk about parallel plates today. We'll do an introductory parallel plate lesson. So what is a parallel plate? It is basically just two parallel charged surfaces sitting next to one another. And they can either have the same charge or they can have opposite charges. And depending on what the charge is, will affect how a charge passing through them or placed in between them will be affected. So let's just do like a quick little review here of some stuff that we've learned in the past. Remember, W, which is work, is equal to the force multiplied by the displacement, something that we learned back in the momentum, work, and energy section. So when you do work to lift an object in a gravitational field, the work that you do is equal to the change in the gravitational potential energy. Okay, so if I lift an object off the ground, well, the work that I'm doing is equal to the change in that energy, right? Gravitational potential energy is just how high I'm holding something. Remember, mgh. So the same idea applies to parallel plates, and it won't be that hard to see. And we don't call it gravitational potential energy, we call it electric potential energy. Okay, and how this works is if you imagine that you place a positive test charge between two oppositely charged parallel plates, well, if one of them has a positive charge and one of them has a negative charge, which way is that positive test charge going to want to go? If I have two parallel plates like this, and the top is all positive and the bottom is all negative, and I place a positive test charge in there, which way is it going to want to go? Even forgetting about this one, which way, what is this going to do? This is going to push it this way. And then to compound with that, it's also opposite charges attract, going to pull it that way. So if I wanted to then push this charge this way, I would have to put in some work, right? I'd have to do some work to be able to move that charge towards the positive plate and away from the negative plate because it doesn't want to do that. So the basic same concept is trying to lift something up. It doesn't want to be lifted up. It wants to fall down, right? So the work done to move the charge is called the electric potential energy. E with a little subscript E. Kind of hard to read on your notes. E with a little subscript E. I also like to write it out sometimes as EPE, electric potential energy. Okay, so what does this formula look like? Where does it come from? Well, let's use a couple formulas that we've already seen. W equals F times delta D. This is force times displacement is equal to the work. Let's write that up. Work is equal to the force multiplied by the displacement. Now, in our case, the force that we're talking about is the electric force, right? Fe. The work is equal to the electric force multiplied by the displacement, right? We have to move against the electric force. And then also remember that electric force is equal to the charge multiplied by the electric field. This is going to start to get kind of, we got a lot of new terms. That's kind of what I was talking about. Now, what we can do though, is we can say, okay, well, I've got electric force here and electric force here. So let's take what electric force is equal to Let's plug it in right over here. And what you end up getting if you do that is that W is equal to Q E times delta D. Now, another fancy term for work is just, remember, it's the change in the electric potential energy. So delta E with a subscript E, right? Remember, work is always equal to the change in the energy, right here, is equal to Q times E times delta D. So that is our new formula. Delta E with a subscript E, or you could call it delta E PE if you prefer, is equal to Q, the charge, multiplied by E, the electric field, multiplied by delta D, the displacement. Let's do what we always do. Let's just write out, you know what, let's even do this. We'll make it a little bit quicker. We'll say this is electric potential energy. What do I always measure energy in? Joules. This is my charge. What do I always measure charge in? Not always, but usually. Coulombs. This is a tough one. What do I always measure electric field strength in? Remember, it's equal to the force over the charge. So it's newtons per coulomb. And then my displacement, that's probably the easiest one. We're measuring in meters. Okay? Now, a really kind of interesting thing here is that if you look at this, coulomb is on the top and coulomb is on the bottom. So those coulombs cancel, and it ends up with just Newton meters. Where else have we seen Newton meters before? Can anybody remember? F times delta D, right? Force times distance or displacement, Newton meters. So it's the same thing, it's work. And work is equal to the change in energy, which is measured in joules or Newton meters, whatever you prefer. Okay? So electric potential. We got a whole new thing. We just learned about a new thing. Now we're learning about another new one, and we're learning about two new ones. What is electric potential? The electric potential is the electric potential energy per unit charge. It is exactly that. So remember, delta means change in. So the electric potential difference, or the potential difference, is the change in the electric potential between 2 points. In other words, the electric potential changes when a charge is moved between 2 points, right? If I move it closer to that parallel plate that is positive, it's going to have more electric potential stored within it because it's going to want to move even more. So the electric potential difference is how much it changes. So electric potential and potential difference can be used interchangeably in the same formulas, and they can be used to calculate the electric field between two plates. That's all new. That's all like weird and foreign stuff that we haven't really seen before. But when I show you the formula, it will make more sense. Okay. Now, the electric potential is the potential energy per unit charge. So electric potential, we are going to use this formula for the electric potential. So what the electric potential tells us is it tells us what the electric field is. We can use it to calculate the electric field. So this is where it gets weird because electric potential is actually given to us by a V. Now, normally we see V and we think of velocity. Not in this case. This is uppercase V. Uppercase V is electric potential. Uppercase V with the delta in front of it is electric potential difference. And the relationship is like this. The electric field is equal to either the electric potential difference or you don't have that delta, delta V, capital V or uppercase V, divided by delta D. So it's the electric potential difference, and then also it's important how much you moved it. And that's kind of what we set up here, right? So when a charge is moved between 2 points, that just means the distance between those 2 points or the displacement between those 2 points. Now, here's where this comes into play, where it says that it's the electric potential energy per unit charge. So when I show you here what this is measured in, it'll make sense. Electric potential energy is measured in joules per unit charge. What do I always measure charge in? coulombs. So joules per coulomb. Now, this is another one of those scenarios where we had, right, we had like when we were learning about newtons for the first time, we had kilograms times meters per second squared. But we had a nice, easy new term to be able to use that. We just use newtons. Well, we have another one for this. It's either joules per coulomb, or we can use the term volts. And volts, we actually just give, this is one of those scenarios where you end up having 40 V. So the unit of measurement is actually the same as the variable that we use to talk about it. So, so we can either use volts, okay? Now, do I need to mention, I'm just looking at my notes here. Yeah, okay, so I need to just mention, no, okay, that's coming on the next page. Perfect. So we won't go there yet. All right, now let's move on. We've got a few more things to talk about here. Electric potential energy. So electric potential energy, which is what we've been talking about this whole page, can also be calculated if I combine these two formulas together. So let's do that and let's see how we can get a new formula. So let's rearrange this formula here to be in terms of electric field, because we have electric fields. We're going to want to set them equal. So E from above is equal to the electric potential energy, so E subscript E, divided by Q times delta D. I'm just moving those to the other side. So E is equal to E subscript E divided by Q times delta D. Now what I do is I take this and I plug it in right there. Maybe don't circle that if you want to just have that formula not have something written on it. But I'm just showing you where this is coming from. So now delta uppercase V divided by delta D is equal to the electric potential energy divided by the charge multiplied by the displacement. And look at this. If I move this delta D up to this side, they are going to cancel, which is nice. So now what we have is we have the electric potential difference, or the electric potential. So it can either be delta V, or I'll leave some space here for a little, or it could just be V. And it's either equal to the electric potential energy divided by the charge, or in this case, it's actually the same thing, the electric potential energy divided by the charge. Okay, so it's either the electric potential difference or the electric potential. So in one case, I'll tell you what it was at one point, and then you have to find what it is at the next one. And if I ask for the electric potential difference, you subtract them. In the other case, I'm just going to ask you what the electric potential is at a given point. So we are learning lots of new stuff today, lots of new concepts, lots of new terms, lots of new units of measurement. And I say that because if learning new terms and new concepts today wasn't enough, let's learn a new unit of measurement as well, and then we'll finish it up. So this new unit of measurement is to measure energy. And it's more closely related to when we're talking about potential difference and electric potential. It's called the electron volt, EV. So lowercase e, uppercase V. It's another unit of energy that's sometimes used. So 1 electron volt is actually, its technical definition is the amount of kinetic energy that's gained by 1 electron that passes through a potential difference of 1 volt. Actually kind of makes sense. Every time you have an electron pass through 1 potential difference of 1 volt, however much energy it gains there, that's an electron volt. So what happens? What is that? What is that actually? 1 electron passing through a potential difference of 1 volt. Well, that's 1 EV, and it's equal to 1.6 times 10 to the negative 19 joules. That doesn't ever change, okay? That's a constant. I don't know why I made my square so big there. So that is something that does not change, okay? So we can remember that. I think I'm certain it should be. You can double check for me and let me know if I'm mistaken, but that should be on your formula sheet. Okay? Don't be confused. A volt is not a unit of energy, but an electron volt is. A volt is a unit of potential, electric potential. An electron volt is a unit of energy. And I know you're probably sitting there thinking, what the heck is Mr. Becker talking about? I'm learning all sorts of new terms. I can't keep track of them all. Let's do a quick little review here, and then we'll end the video for the day. Okay, so let's review all the new terms and symbols that we have learned. What is EE? Or like I said, sometimes it's EEE. That's a little bit easier to remember what it actually is. Electric potential energy. Okay, so electric potential energy. Now, one other thing I just want to mention is when we have two different units of measurement for energy, that means that we have to be comfortable in doing a conversion between those in certain questions. Prepare yourselves for that, okay? So when I'm measuring energy, energy can either be measured in joules or electron volts. That's the new one that we learned. Okay. What is E? One of the first ones that we did. Electric field strength. How do I measure electric field strength? Try to see if you can remember that. Remember, it's force divided by Q, F over Q, newtons per coulomb. Or if we're using ECs, it's newtons per EC. We're almost done, halfway there. What is V? Electric potential. Electric potential. What do we measure this one in? You should be able to remember this. We just did it. Volts, right? Or what was the first one I said? It was energy over charge, right? So joules per coulomb. Okay, and then the last one, very, very similar, just has the difference in there. So electric potential difference. So things are getting a little bit wacky, a little bit more weird than they were when we started. That's kind of what happens in this course. We get a little bit more, obscure, not all just mechanical physics. So this one's measured in volts or joules per coulomb as well. A little bit harder to picture what's actually going on. Great question. Yes, we can actually measure this in joules per EC as well. So this could also be like the newtons per EC. And it could also be, whenever we have joules, we can also replace it with EV too now, right? Electron volt. So this could be electron volt. This one's kind of combining a whole bunch of different ones. So yeah, like I said, things are a little bit weirder. Things are less easy to kind of picture exactly what's going on. So right now, more than ever, it's just very important to just make sure that you're keeping up trying to practice problems and just getting as used to them as you can. Because not even doing the practice problems and just trying to figure it out in your head is going to be, I don't know, I think personally very difficult. So don't rely on that. Now, you have a long weekend, so that's great. On Tuesday, we'll pick back up. We'll do the actual parallel plate examples together. But that was definitely a long enough lesson. I hope you have a great long weekend and take care of yourselves. And I will talk to you on Tuesday.